Hi guys, my name is Mark. I'm studying engineering at Trinity College Dublin, and in today's video we're going to tackle the higher level physics 2020 paper. Specifically, we're going to be looking at question 1, which is worth a total of 40 marks. It is part of the multiple choice experimental section on the paper, and question 1 tends to be based around mechanics, and in this case this question is on the conservation of momentum. Let's get straight into the question. In question 1, we are told that there's an experiment that has been done to verify the principle of conservation of momentum. Body A was set in motion with a constant velocity. It was then allowed to collide with a second body B, which was initially at rest, and the bodies moved off together at a constant velocity. The following data was obtained. Mass of body A is 125.6 grams. Mass of body B is 111.1 grams. The distance travelled by A for 0.2 seconds before the collision is 11.4 centimeters, and the distance travelled by A and B together for 0.2 seconds after the collision was 6.1 centimeters. Using this information, we're going to be asked several questions, but normally the first part and the second part tend to be about the experimental method and understanding how the experiment was conducted. In this case, we are asked to draw a label diagram of the apparatus that was used in this experiment. Now I'm going to highlight an important word in this section. It is the word labeled. It is incredibly important that you label your diagrams, because although you might know exactly what's going on, if you forget to label your diagrams, you're losing most of the marks straight away. For part I here, I've drawn out the appropriate diagram. What we see is two carts sitting on an inclined plane. The importance of this inclined plane is that it is at an angle so that the carts remain at a constant velocity. The entire point of the conservation of momentum is that the velocity is kept constant before and after, so we cannot have any acceleration. That's why the angle of this slope is very important, so we don't get any acceleration in the carts. We have two carts, cart 1 and cart 2, and the important piece here is that there is a piece of Velcro between them. The reason for this is that when the two carts collide, they're going to stick together and move off as one cart. Also in this section, we're going to see our ticker tape counter and our ticker tape. The reason for this is that this is the method we use to measure the velocity of the carts before and after. The ticker tape here is coming out of our ticker tape counter and is connected to the back of cart 2 with a small piece of tape. How to power the ticker tape counter is always another question that comes up, and in this case it's by a small power source that we've connected here. In this case I've written 3 volts on it, but it doesn't really matter what you write on it. It doesn't matter the number of volts, just that you label it that it is the power source. In this question, 3 marks were going for labelling cart 1 and cart 2. And for the 3 marks were for the Velcro mean of attachment. Basically, we were getting 3 marks here for labelling how the two carts would stick together after they collide. And you got your final 3 marks for talking about the method we use to time the device. In this case, it's going to be our ticker tape counter. Scrolling back up to part 2, we see that we're asked now to describe how the time interval was measured. In the diagram above, we talked about how the ticker tape and the ticker tape counter were used to calculate the velocity before and after. And the reason that they were able to do this is because they were able to be used to record the time. But here we're now going to describe how they record the time. Taking the ticker tape after it's been used by the machine, we see that there's going to be a series of dots. Disregarding the dots at the immediate start and the immediate end, this is done because sometimes there's inaccuracies at the start or the end as the car is slowly speeding up or slowly coming to a stop. We have to pick a cluster of 3 dots nearing the start and nearing the end. We can use each of these clusters then to find important pieces of information. For example, by measuring the number of gaps between the central dot in both of these small clusters, we can find the time. We do this by multiplying the number of gaps by 1 over 150. The reason for this is that each gap here represents 1/50th of a second. By multiplying 1/50th by the number of gaps, we are able to find the total time between the initial velocity and the final velocity, or in this case, the total time here. This part of the question was worth only 6 marks in comparison to the 9 marks of the last one, so you can see how important it is to be able to label your diagrams. The 6 marks here were going for talking about the number of gaps. In this case, you got 3 marks. And finally talking about the 1/50th of a second, or 0.02 seconds. This was how you got your other 3 marks. These pieces of information are very important to finding the total time, and that's why they were given the most marks out of the question. In part 3, we were asked how are the effects of A, friction, and B, gravity minimized? The answer to this is a simple theory question, and it goes as follows. Friction can be minimized by sloping the track. As well as this, gravity is then minimized as the frictional force felt by the body as it goes down the track cancels out with the acceleration. If you think about it, if we place a rider, or a cart in this case, on our track and we allow it to roll down, it will accelerate at some given acceleration. However, the friction in this case can be assumed to cancel out this acceleration, and it means that gravity in this case is then minimized. In terms of friction being minimized, by using a sloped track, we minimize this effect of friction. This question is worth a total of 6 marks. You got 3 marks for saying that friction can be minimized by using our sloped track, and you got another 3 marks for saying that the gravitational force can be minimized by using the frictional force to cancel out the acceleration. This gives us our total of 6 marks for this question. It must be noted that another way that you could minimize friction is by using something called an air cushion. This can be done on horizontal tracks by using a different method known as light gates. But for the purposes of this experiment, we're going to be talking about the ticker tape timer method. Now that we are coming to the end of our question, we normally have a few calculations we have to do, and this normally takes part in part 4 and part 5. In this case, we are asked to calculate the initial and final velocities of body A. In part 5, we are asked to demonstrate how the experiment verifies the principle of conservation of momentum. So let's start with part 4. In order to find the velocity before and after the collision, we must use the information given to us in the question. What we know is that the mass of body A is 125.6 grams. We also know the mass of body B, which is 111.1 grams. And finally, we know the distances travelled before and after the collision. We are going to use these in our calculations to find the velocity before and the velocity after the collision. I always find it personally helpful to write down the information that we have at the start of the question down near where we're doing the calculations. This is because it helps me to not get confused going back and forth between the first bit of the question and the last bit of the question where the calculations are. Here I've written down the mass of body A, the mass of body B. We've also written down the distance travelled by A 0.2 seconds before the collision and the distance travelled by both A and B together 0.2 seconds after the collision. We're going to use this information to find our initial and final velocities of part A, which is what we're asked for in part 4 of this question. I'm now going to use one of the most useful formulas in mechanics. It is V equals S over T. What this means is that the velocity of the body is equal to the distance it travels divided by the time. We're going to use this to find our initial velocity of mass A. We know the distance travelled by A 0.2 seconds before the collision. We are given a time and we are also given a distance. By plugging this into our formula, we are able to find the velocity of A just before the collision, which is our initial velocity. Here I've plugged in the information that we know. One difference though is that I have converted our 11.4 centimeters, or our distance travelled, into meters. I've done this by dividing by 100. The reason for this is that you always do these calculations using SI units, and the SI unit for displacement, or S in this case, is going to be meters. So we need to convert our centimeters to meters before we can divide by the time. Now that we've done this, we see that 0.114 divided by 0.2 should give us our velocity. By plugging this into our calculator, we find that our initial velocity is going to equal to 0.57 meters per second. Another thing to note here is how important the units are. Because we are dealing with velocity, the unit for velocity is meters per second. You can write it as m meters times second to the power of -1, or you can also write it as m over s. Personally though, I almost always write it as ms minus 1, but they are completely interchangeable depending on how you like to do your maths. For the second part of this question, I'm going to apply the same formula to the information that we're given. We know the distance travelled by the body 0.2 seconds after the collision, and we know the amount of time it took. By using the same formula and plugging it into the calculator, we can find our answer for our final velocity. Here I have written out all the information we know, plugged it into our formulas, and found that our final velocity is equal to 0.305 meters per second. These are our answers to part 4 of this question. In this question, there was 9 marks going, and you got 3 marks for remembering our formula for velocity. In this case, V equals S over T. You got another 3 marks for writing down, or should I say substituting, the information that we know. The important thing to note here is that you must convert your centimeters to meters, because all our calculations, like I said earlier, are done in SI units. So it is incredibly important that we convert all of them to meters. Finally, we got 2 marks for writing our initial velocity as 0.57 meters per second, and we got our last mark for finding our final velocity, which is 0.305 meters per second. Now moving on to part 5. Going back to our question, we were asked to demonstrate how this experiment verifies the principle of conservation of momentum. Before we do that though, let's familiarize ourselves with the conservation of momentum formula using our log tables. By going to page 51 of our log tables, under our collision section, we'll find our formula for the conservation of momentum. Our formula for our conservation of momentum is m1u1 plus m2u2 is going to equal to m1v1 plus m2v2. m1 and m2 in this case are going to represent our masses for body A and body B, and u1 and v1 are going to represent the velocity of those masses before and after our collision. Since there are two bodies, A and B, that's why we have two masses, 1 and 2, and two different velocities, u1, u2, and v1 and v2. Here I've rewritten the formula that we found in our log tables. Now what we're going to do is plug in the information that we know. Recalling our question, we were given our mass for A and B, and in the last section, we just found our initial velocity and our final velocity. What we're now going to do is sub in the information that we were given. Here I've subbed in all the information that we know. In the first term, we have m1 and u1. m1 in this case is going to be the mass of body A. The mass of body A was given as 125.6 grams. As I was saying earlier though, we need to convert everything into our SI units, and the SI unit for mass is kilograms. So therefore we have to divide our grams by 1,000 to convert into kilograms. u1 in this case is information that we found out in the first section. It's going to be 0.57 meters per second. For the second term, we have m2 times u2. The mass of m2 is 111.1 grams, and once again, we are dividing by 1,000 to convert this into kilograms. We are also going to be multiplying this by u2, which in this case is 0. The reason that we multiply by 0 here is because the velocity of the second one is 0 as it is staying completely still. This is because in the question we see that one cart is going to collide with another cart that is staying completely still and stationary, and this is why the velocity of the second car is 0. In our third term we have our mass once again multiplied by v1. We found that out earlier, and we also have m2 times v2. Another thing to note here is why these two numbers are the same, and that can be put down to the fact that when these two particles, or should I say, when these two carts are going to collide, they're going to move off together as a single unit. This is because the Velcro we talked about in the first section when we were doing our diagram. When the two carts are going to move off together, it means that they're going to stick together and have the same velocity. That's why the velocity we found earlier is going to be the same for both m1 and m2. By summing this in and multiplying out with a calculator, we can verify the principle of conservation of momentum. Plugging the information into our calculator, we are going to find that the momentum on the left-hand side before the collision is going to equal to 0.072 kilograms per meter second, and on the right-hand side after the collision, when the two carts move off together, we find that the velocity, or should I say the momentum, is 0.072 kilograms per meter second. This proves the law of conservation of momentum because the momentum before is the same as momentum after when we minimize the effects of external forces, like the resistance and gravity that we talked about earlier. For part 5 there was 10 marks going. This is because it was the most calculation heavy section of the question. You got 3 marks for remembering our formula for momentum and the conservation of momentum. You got another 3 marks for subbing in the information that we know. This is onto the left-hand side and the right-hand side. Finally, you got 2 marks for showing that they are 0.72 kilograms per meter per second each, and you got 2 more marks for verifying that they are equal to each other, giving us a grand total of 10. Ultimately, this question on mechanics is one that some people don't like and some people love, and I personally find it's a great way to pick up marks because a lot of the question is spent doing diagrams and answering simple experimental questions, and it is less calculation heavy than you might give it credit for. Thank you for listening. Cheers.